Is this yours?
No. Be careful about the adjustment of the camera. Okay. Okay, so I think now everyone is there. Thank you. Good morning. Now today we want to start actually this lesson. For some reason, in Swedish book they have delayed this. Actually, I was expecting this in Math 1C, but they have decided to put it in Math 2C. So congruence is actually means that you have a shape. You have two identical copies of the same shape. Actually, essentially everything from the first shape is exactly equal to the other shape. So that is the meaning of congruence. Yes. So I don't know if I have a triangle, a pentagon, and everything, and if I copy and paste it exactly the same copy, that would be congruence of these two pictures. Yes. So that's the meaning of congruence. But mainly we want to talk about the congruence of triangles. Okay, we want to see that when two triangles are congruent. Okay. Yeah, it is clear that if two triangles, if I have two triangles, if they are going to be the same copy of the same picture, they have to be really identical from every aspect. Yes. So A, B, C. Assume that this is your triangle. If I want to have a triangle which is congruent to this triangle, it means that I need to be able to copy this exactly and paste it somewhere else. Of course, I can rotate it around. That is no problem. Yes. But let us keep it like that. So then this would be another triangle. Of course, here it is a little bit hard if I want to draw exactly the same picture, but you need to be able, you need to understand, I mean exactly the same copy. So for example, this one, let me call this one, I don't know, M, N, and P. If they are identical copies of the same picture, we say that these two triangles are congruent. And if I want to show it by mathematical symbols, I would say that the triangle ABC, the symbol that you use for congruence is equality, and then you have this on top of that. Yes. So we say that the triangle ABC is congruent to triangle MNP if and only if I can take it and put it exactly on top of that so that they exactly overlap. Yes.
Doesn't it mean that they are similar and equal?
Yes, automatically they are similar. Yes, because they are identical, so they are similar.
I think about the lines you wrote, the congruent. Okay.
No, I mean that. Yeah, you are right, but yeah, I don't know why they have used this. If you are talking about why they have used this, I really don't know. But that's the symbol that we use. This. So what we know is that if two triangles are similar, there is no guarantee that they are congruent because one of them might be smaller, the other one would be bigger. Yes. But if they are congruent, definitely they are also similar. So congruency is a more stronger condition. Yes. Okay. So we can say that if two triangles, let me write this as a remark. If two triangles are congruent, they are also similar. But not the other, but not necessarily the other way around. So So what is the immediate consequence of this statement? If someone tells you that I checked it exactly, this triangle is congruent to this triangle, what you can conclude? You can conclude every corresponding piece, every piece of this triangle is equal exactly to the corresponding piece of that triangle. Yes, that's the meaning, because they are the same, the copy of the same picture. So, for example, if you want to, you can conclude that side AB is equal to side MN. You can conclude that, I don't know, side AC is equal to side MP. You can conclude that side BC is equal to side MN. You can also talk about, for example, the corresponding angles. The angle A is equal to angle M, the angle B is equal to angle C, and the angle B is equal to angle N, and the angle C is equal to angle P. And of course, if you want, for example, if I draw a height, if I draw the height here, if I draw this corresponding height here, the height of this one is exactly equal to the height of this one. So they are exactly the same picture. So whatever you have here in one of them, you have to see the other one. Yes?
Are you sure that BC equals to MN?
No. AB is equal to MN, AC is equal to MP, BC is equal to NP. Thank you.
You are welcome.
And then let me make A is equal to M, B is equal to N, C is equal to. Okay. But we have three theorems, so that we want to discuss about that today. And then it tells you that you really don't need to check all of these conditions. Of course, it is clear that the other way around is also true. If someone tells me that these two triangles are congruent, I definitely can conclude that every piece of one of them is equal to the corresponding piece of the other one. And if someone tells me that these 6 conditions hold, then it means that they are the same triangles, yes? Because it is clear that if the angles and everything are the same and the sides are the same, they are the same triangles, yes? So this is the other way around is also correct. But then, as we want to learn today, we don't need to check all these 6 conditions. Some of these conditions are enough. Okay, 3 of these conditions are enough, but you need to be careful about which conditions to choose. Okay, so let us do them one by one. So we have 3 theorems, so statements or theorems. So theorem 1. So the first thing is telling you that if you have 2 sides from one triangle is equal to 2 sides of the other triangle, and the angle between those 2 sides is also equal to the angle between the other sides of the other triangle, these 2 triangles are congruent. We really don't need to check everything else. So how should we write this? So it's better to write it like this instead of writing it in words. Might be in figure, it's easier to understand. So, for example, if I have triangle ABC, and if I have another triangle, so it's a little bit hard to. So yeah. So make sure that you understand everything that I want to draw. It should be identical. So let me call it MNP. Okay. So of course, if you check all these 6 conditions, it is guaranteed that this triangle is congruent to that triangle, but you don't need to check all of them. This first theorem tells you that if you just check the equality of this one with that one, and if you check the equality of this one and this one, and you just check the equality of the angle between these 2, yes, and the angle between these 2. If these 3 matches correspondingly, then automatically these 2 triangles are congruent. You don't need to check others. So what I'm trying to say is that automatically this angle becomes equal to that angle, which is not trivial. And this angle also becomes equal to that angle, and this side also becomes equal to that side. So this is called side angle theorem. Side angle side theorem. So let me write it, and then you need to write it in this way: side A angle side. And it is extremely important to put A between these two sides when you want to refer to this theorem. Side angle side. It means that sides are on the extremes, and the angle is between them. Yes.
Would you say that these triangles are sassy?
I don't know. Okay. So this is the first theorem. For this one, I should be able to convince you that this is the case. It's not hard at all. So what I want to convince you that if this AB is equal to MN, and if AC is equal to MP, and if angle A is equal to angle M, then I can take this and put it exactly on top of this so that they 100% overlap. Okay, so assume that this is a rigid object. You are taking it out from the whiteboard. And then because AB is equal to MN, so you agree with me that I can put MA on top of M, and because AB has the same length, B will be exactly on top of N. Is that understandable? I'm just taking it out. But what happens for this side? Because this angle is equal to that angle, when I put this triangle here and I fix AB on top of MN, because this angle is equal to that angle, this side definitely lies on this side. Yes? Is that understandable? But because on the other hand, the length of this one is also equal to the length of this one, where C will land, where C will be by this overlapping, it's clear that C will be on top of P, yes? And then when B is on, so A is on top of M, I put it myself there. And then I claim that I can put B on N, yes, because this length is equal to that length. And then because this angle is equal to that angle, this side will definitely lie on this side. And because this length is equal to that length, then definitely C will lie on top of P. Okay, so A is on top of M, B is on top of N, and C is on top of P. So automatically BC will lie exactly on NP. Yes? So it's important. It's easy to understand that if this condition holds, I can take one triangle and exactly put it on top of that. So it is extremely important. Two sides from one triangle are equal with two sides of the other triangle, and the angle between those two sides should match with the angle between those two sides from the triangle on the other side. So if this is the case, I can conclude that this triangle is congruent to this triangle, and whenever you want to use this theorem, you should refer it as SAS, means side angle side. And of course, this is not only this one, any two legs. For example, let me consider this. Yes, if someone tells me that I have two triangles here, for example, let me draw it the other way around this time. Yeah, but drawing it is a little bit hard, but let us assume this case. For example, if someone tells me that this side is equal to this side, and this side is equal to this side, which angle should I consider if I want to use SAS theorem? The angle between these two sides. So someone should tell me that alpha is equal to beta. Let alpha and alpha. If this one is equal to this one, and this is equal to that, and this one is equal to this, then what I have two sides and the angle between them of the first triangle matches with two sides and the angle between them of the other triangle. So they should be the same copy. They should be the copy of the same picture. So this is called SAS. So the way that we understand this problem, if someone asks you why this theorem is true, because we just convinced the person that we can take it and put it exactly on top of that. Yes? So you see, I really don't need to check the other one. So here, can you tell me, if this is equal to that, if this is equal to this, and if this is equal to this, can I conclude that angle C is equal to angle P? Yes, because they are congruent. When they are congruent, it means that all pieces of one of them is equal to the other, the corresponding piece of the other. So that's very important. As soon as you can convince yourself that these two triangles are congruent, you immediately conclude that whatever you need from the left triangle is equal to the corresponding piece of the right-hand side triangle. Okay, so this is one thing I want you to know. For example, if I want to give you an example, it's a little bit, I don't know, should I give these examples? They are very simple, but it's a little bit confusing. So what I want to show is that if I give you a quadrilateral and I give you just one piece of information, the diagonals of this quadrilateral actually bisect each other. Then I want to conclude that this quadrilateral is parallelogram. Okay, so this is, you see, this is a very important concept. So here, I have a quadrilateral. Of course, I have now, if this is the confusing part, because I know that this will happen, I need to draw it if I want to show what is happening. So I need to draw a parallelogram, but still I don't know if this is a parallelogram. It's a little bit confusing, but you can understand it immediately. So I draw something, I draw a picture for you. You immediately see, if I ask you what the shape is, by the way, you are not certain about that this is a parallelogram. Yes, it looks like a parallelogram, but might be it is not, because how should I really know that they are 100% parallel? And how should I know that these are 100% parallel? We don't have any guarantee for that, yes? But I give you one piece of information. I give you this information that if you draw this diagonal, and if you draw this diagonal, I tell you that these two diagonals bisect each other. So for example, I would say that this is equal to that, and I tell you that this one is equal to that one. If I give you this piece of information, then you are 100% sure that this quadrilateral is indeed a real parallelogram, 100%, yes, without any deviation from being parallel, yes? So do you understand what's going on? So I give you a quadrilateral. If I want to give a picture, so if I draw the quadrilateral like that, then it would be hard to convince you that they are bisecting each other, yes? Because this cannot happen in reality. In reality, if this is going to happen, the quadrilateral has to be a parallelogram. So what I'm trying to tell you is that let us assume that I have a quadrilateral. For the time being, I am not certain about that if this quadrilateral is a parallelogram. But I am certain about something. I know that if I draw the two diagonals of this quadrilateral, then they bisect exactly each other, yes? Now I want to conclude that this quadrilateral is indeed a parallelogram. Okay, how can we do that? How do you show that a quadrilateral is a parallelogram? What is the definition of a parallelogram? Do you know that? How do you see that this is a parallelogram or not? Yes?
Well, the definition is a quadrilateral where two sides are parallel to each other and the others are also parallel to each other.
Yes, that's the definition of a parallelogram. Yes? A quadrilateral is called a parallelogram if the opposite sides pairwise are parallel. Yes, that's the meaning. So if I don't know this is a parallelogram and I want to show that this is a parallelogram, I have to convince everyone that this side is parallel to this side and this side is parallel to that side. If I can convince you of that based on the information that I have on the picture, then I am done. Is that understandable? Okay, but how can I use? I can use this SAS theory. How should I do that? Because let us call this
can
O.
I say?
Pardon?
Can I say?
Yes, yes.
Yeah. So they share the same angle because it's like an X. I don't know what to call it. So they.
No, these are learn this name.
angles,
It's
so
called
would be-
vertical. Yes. So here,
Yes, vertical. So they share the same angles.
it's not called this. They are not the same angles because this angle is this one, this angle is that one, but they are equal because they are vertical. Yes. So let me write what
Yes.
Rocco is saying. So I would write the angle O1 is equal to angle O2. If you want to be very clear, I would write vertical angles in front. I'm explaining to the person who's reading my text vertical angles. Okay? Okay, so this is clear. And then, can you continue yourself, Rocco?
Well, it's the same for the other.
No, but don't jump into the others. So what is your goal? If yes, you are right. This one is also this equal to that one. Then what?
Okay. So we know then that the two triangles are congruent.
How? You need to convince me. Yes.
So
OA.
the rule you taught us.
Yes.
that,
You need to write them. I know even if it is trivial, but in the exam you have to write them. You should say that OA is equal to OC. Why? Because you told me that they are bisecting each other. So this is why I can write OA is equal to OC. And similarly, I can write OD, yes, is equal to OB. Yes? Now, based on these three pieces of information, this one was given to me by the problem. This one was given to me by the problem. This one, I used my knowledge about vertical angles. So all these three statements that I have written here is completely true, based on the information in the problem and my own knowledge. Now, can you see that this is a triangle? This is also a triangle. Yep. Two sides from the left-hand side triangle are correspondingly equal to two sides of this triangle, and the angle between these two sides from the left one is equal to the angle between those two sides from the right one. So this is exactly SAS theory. Yeah, so you need to write something like this, and then you would say that from these pieces of information, I can conclude based on SAS. You don't need to write side, angle, side. We just refer by this, I understand what you mean. So you should write SAS, or if you want, you can put dots. It's abbreviation, okay. So SAS, we can conclude that the triangle OAD is congruent. Don't get confused. You need to write the symbol of congruency in this way. Is congruent to the triangle OBC. But why, Rocco or anyone else? Can you tell me why this is useful? My goal is not to show that this triangle is equal to that one, congruent to that one, even though it's a true statement. But how is that useful? Remember, my goal was not to show that these two are congruent, even though they are. But my goal is to show that this side is parallel to this side, and this side is parallel to this side. How can I use now this to show that these are parallel? So that's the point. So Rocco, what was your strategy when you said that, okay, these are congruent? So what is the benefit of knowing that these two triangles are congruent for the purpose that I have in the problem?
Yeah, so you know that then that the sides are all the same.
They are the same. Yes, you are right. You can conclude that AD from length point of view is equal to this one, but this doesn't guarantee. Even if I show this one is equal to this one, which is true, and I show that this one is equal to this one, there is no guarantee that it's a parallelogram. Yes?
Okay, well, it's a start at least.
Okay, but you need to complete it. If you want to go in that direction, you need to complete it. Because equality of this one, you are true. So if I conclude that this length is equal to that length, that I agree with you. Because after this, it's an immediate consequence that this length is equal to that length. But equality, even though it's true for parallelogram, it's not 100. If I show that this one is equal to this one and this one is equal to this one, do you think that this is a parallelogram? Yes or no?
Well, they still have to be parallel.
No, because for example, let me draw. No, they are not the same. So can you imagine a quadrilateral that two sides are equal but they are not
Equal but not parallel?
yes.
No.
Shouldn't we have that?
Maybe a quadrilateral, equilateral triangle.
No, it's not a quadrilateral.
No, equilateral triangle.
Equilateral triangle is it? I want to have a quadrilateral,
Okay.
not a triangle. Yes. I don't know. Might be. But what I understand is that just equality of these things doesn't guarantee that this is a parallelogram. Yes.
Actually, when you look at a trapezium,
Yes.
when the top and bottom, the opposite sides are parallel,
Yeah, this one I agree
and then
with you.
the sides are equal but not parallel.
Yes, you can draw these two sides equal but not parallel. So, and this is not a parallelogram. But the point is that these are not equal. So if they are, so
Well,
look,
I have an idea.
yes, yes, please.
So you can imagine AD and BC as two parallel lines, if we say that they are.
Yes.
And we can imagine the line AC as a what you call transversal.
Yes, exactly. So that's you are telling me the real. You are telling me the proof. Yes, I agree with you. That's correct. So that is my point. So I want to, from here, instead of concluding that AD is equal to BC, which is of course true, let me conclude something else. Can you tell me what can I conclude about this angle? Let me call it A1, and this angle. Let me call it C1. From here, what can I conclude about the sizes of these two angles? Can you tell me? If this triangle is congruent to this triangle, it means that all corresponding pieces of one of them, all pieces of one of them is equal to the corresponding piece of the other one. Yes?
I think of the Z, the parallel and the transversal Z, when you can prove that.
No. Just I'm asking you one simple question. What is the connection between A1 and C1?
They're the same.
Okay, so that's, you have to write that. So A1 is equal to the C1. Now, what happens, it means that I have a shape like this. I have some lines like this, and I'm guaranteed that this angle is equal to this angle. So it means that I have my Z. Yes? Because be careful. If you have your Z, you can conclude these angles are equal. If someone tells me that these angles are equal, I can conclude that these two lines should be parallel. So one of them is the theorem, the other one is the converse of the theorem. Yes? So be careful. If I draw a line like that, and I tell you this line is parallel to this line, if you want to, you can conclude these angles are equal. Opposite way. If I draw something like this, and I don't tell you that these are parallel, but I tell you that this angle is equal to that angle, then you can conclude that these two lines are parallel. Be careful. One of them is the theorem. The other one is the converse of the theorem. So exactly, now I can conclude that AD is parallel to BC.
But that doesn't necessarily prove that it's a parallelogram.
No, not yet.
Yeah.
We just know that these two are parallel. But we can just do the same thing with these two triangles. Okay? So what we have to do, we can go and write, this is, for example, O3. And this, let me just put it double. And then this is O4. Repeat the process, but instead of from, so I would say that to O4. And then you told me that, I don't know, for example, OA is equal. And then you told me that O is equal to OB. But again, using the same theorem, SAS, I conclude that the triangle on top, OAB, is also congruent to the triangle ODC. Then this means that, again, with the same strategy here, so let me call this one A2 here, and let me call this one C2. Now you see that I have this picture now, something like this, yes? And someone tells me that this angle is equal to that angle. So it means that I can conclude that AB is parallel to, so this gives me that A2 is equal to C2. And this gives me that, okay, AB is parallel to BC. Therefore, what do I have? I know that AB is parallel to BC, and I know that AB is parallel to DC. So I can conclude immediately that A, B, C, D is a parallelogram. Yes? Also, don't get confused. Sometimes we want to prove congruence. We have three theorems that we want to talk today. We just talked about one of them. But the previous lesson, we wanted to show similarity. Then we had two results, angle, if you remember, and which is the most common one. And the other one was the equality of the ratios of the corresponding sides. Is that okay for everyone understanding? Yes? Okay, now let us move on and go to the next theorem. Okay, so here, another theorem that we want to talk today is, let me see, what is the order given here? Okay, so let me go and consider this case. So let me write theorem number 2. We want to consider this scenario. In the previous scenario, we had two sides and the angle between them. This time, I want to have two angles and the side between them. Okay, so two angles and the side between them. So I need to draw exactly the same copy. I try to do my best here. So M and P. So be careful. Here, for example, someone tells you that I measured BC and it becomes exactly equal to NP. Okay? And then they tell us that I measured this angle and it turns out to be equal to that angle. So they measured this angle, and it is equal to n. They measured this angle, and it is equal to p. So you see the situation is reversed somehow. How many angles are involved in this statement? 2 angles. Where is the side lying? The side is lying between the angles, yes? This angle and that angle, I am not considering this side. This angle and that angle, I am considering the including side. This angle and that angle, including side. So the point is that if someone tells me that angle B is equal to angle N, and angle C is equal to angle P, and BC is equal to NP, it is enough. I don't need to check others. Immediately, I can conclude that triangle ABC is angle MNP. And what do you think would be the abbreviation for that? Angle side angle. Yes, so you need to write it in that way. But why this is true, it is hard to convince yourself exactly because of that. Because, I don't know, might be you say that I take it and put it here. Of course, B will be exactly on top of N. C would be exactly on top of P. Of course, this line will exactly lies on this line because this angle is equal to that angle. And this line exactly lies on this angle. And then you convince yourself that this A will lie on N. Yes, but this is not good. Let us do it a little bit better. Okay, how? If someone tells me, so let me write the proof. This is given in the book, and this is interesting, by the way. Because the way that I learned it when I was at your age, I first learned congruency and then learned similarity. But the logic in your book is different. They teach you the notion of similarity first, and then they want to conclude congruence. That's also okay. So here, the proof is nice and simple proof in the book. So let me ask you a question. If someone tells me just this information, that B is equal to N, only this piece, and C is equal to P, okay, can you tell me what can I conclude? Assume that no one tells me about this. I have only these 2 pieces of information. Yes?
They are similar.
They are similar. So it means that based on angle theorem, yes, triangle ABC is similar to the triangle MNP. Okay? But what can I conclude? When they are similar, it means that the ratio of AB to MN should be equal to, okay, can you complete it? AB over MN should be equal to what? Should be equal to?
1.
No, not yet.
Okay.
Why 1? We don't know. I know that they are similar. If they are similar, it means that the ratio of AB over MN is equal to the ratio of AC over MP is equal to the ratio BC over NP. Yes, is that understandable? This we know.
NP.
But now I can use the last piece of information given in the problem. If I ask you what is the last fraction, you can immediately answer because of this extra piece of information. Yes?
1.
That is 1 because the numerator is equal to the denominator. So this fraction is equal to 1 because BC is equal to NP. Okay, but this fraction is equal to 1 again because these 3 fractions should be equal. If the last one is equal to 1, it means the first one and the second one have to be equal to 1 because they are equal. So this immediately gives me this result. This implies that this implies that the first fraction is equal to 1, and the second fraction, what is that? AC over MP is equal to 1. But now, if someone tells you that I saw a fraction which is equal to 1, then what you can conclude? You can conclude the numerator and the denominators are equal. So AB is exactly equal to MN, and AC is exactly equal to MP. So you see, we really nicely were able to get these two results. So if you give me these equality of these two angles and equality of the side between them, I can immediately conclude based on this argument that the other sides are correspondingly equal. But there's one piece that I need to confirm about that. And so you see, now I know that this is equal to that. I know that this is equal to this. I know that this side is equal to that one. I know this angle is equal to that angle. This angle is equal to that angle. There's one thing left to show.
Angle A equals to
But that's automatically satisfied, yes?
Yeah.
Because the sum of the three angles should be 180. If two angles from one is equal to the two angles of the other one, the last one should be also the same. So for example, if I want to write angle N, so on the other hand, angle M is equal to 180 minus angle N plus angle P. But you told me angle N is equal to angle B. So instead of N, I put B. And you told me that angle P is equal to angle C. So instead of P, I put C. But now let us go to the left-hand side triangle. What is this one? This is exactly angle A. So I was able to show that angle M is also equal to angle A. So every piece on the left-hand side triangle matches with every corresponding piece of the right-hand side triangle. Is that understandable?
Yeah.
Yes. So you don't need to be worried about the proof. Proof is important. Otherwise, that's just memorizing and not understanding anything. But this is the second situation which is important. If you can convince yourself of this situation, you can conclude immediately that the triangles are actually congruent. So for example, let me give you an example here. I give you a triangle, yes. And I write I would write that the figure, it might not be into to scale, okay? But I give you another piece of information. So here A, B, C. Okay, so if I ask you what type of triangle do you think it would be, you would say it's isosceles. But no, I'm not giving you that. Might be it is isosceles, might be not. Okay, but what I tell you is that I tell you that I draw the bisector of this angle. I draw the bisector of this triangle, and then continue it until it will intersect with this one. So it means that the angle A1 is equal to angle A2. I am giving you this piece of information. And I am telling you that when I draw the bisector, when I go and measure this angle, it becomes 90 degrees. So you see, this is not under my control. This is not always the case. If I have a triangle, for example, like this, if I just draw the bisector, that's not under my control. It will go and intersect this line with some angle, which I don't know. But I am telling you that coincidentally, it happens that this angle is 90. So I draw the bisector, and it happens to be that this angle is 90. I want you to show me that this triangle is actually isosceles. So this is important. Do you understand what's going on? So here, I am just drawing the bisector, and then when it intersects this side, I measure this angle, and I see this is 100% 90 degrees, yes? And I want to claim that the original triangle is not just an scaling triangle. It is definitely an isosceles triangle. Yes.
We cannot assume that BH equals to HC.
Not yet.
Okay.
No, that's the point. Automatically it becomes, but that is not the piece of information included in the problem. My assumption are two things. I know that A1 in this picture, I know A1 and A2 are the same. I know this angle is 90. Based on these pieces of information, I want you to conclude for me that this triangle is an isosceles triangle. So how can I show that?
Well, they are similar.
Yes, they are similar.
Yeah.
Okay, that's one way. But then, what can you conclude then? If the triangle on the left is similar to the triangle on the right, which is exactly the case, because one angle is equal to this angle. If this is 90, automatically the other one is also 90. So two angles, so they are similar. But similarity is not a good idea here, because similarity just gives you the ratios. Of course, the ratio is also equal to 1 here, and then you can conclude that. But I prefer to use congruency here. Yes, can you see at least we can train our understanding about this new theorem. Can you just tell me why the left-hand side triangle is congruent to the right-hand side triangle? Yes?
Maybe it's because we have two angles that are the same, and we have the line in the middle, which is the same for both
So
of them.
this is now ASA theorem. Exactly. That's what I meant. So here, so you write like this. You write angle A1 is equal to angle A2. You told me. And you told me angle H1 is 90. I myself conclude angle H2 is also 90 because the whole angle should be 180. So let me write here H1 is equal to H2 is equal to 90.
Yes.
And then this AH is common between the left-hand side and the right-hand side. So I would say that AH is equal to itself, common to both triangles. So then you need to write something like this on top of that. So you write angle, side, angle. I can conclude the left-hand side triangle, which is ABH, is congruent to the right-hand side angle, right-hand side triangle, which is ACH. If two triangles are equal, I can sometimes I say equal. So if the two triangles are congruent, it means that every piece of one of them is equal to this corresponding piece of the other one, including AB from the left-hand side and AC from the right-hand side. Is that understandable? So from this, you need to write these details in the exam, okay? ASA. So you concluded that these two triangles are congruent, and when they are congruent, every piece of the left-hand side should be equal to the corresponding piece of the right-hand side, including AB and AC. Yes?
What level problem is this?
Yeah, it's very simple.
Easy.
Yeah, easy.
And how does it?
No, but
how does an A level problem look
you
like?
can see the book.
Okay.
Yeah. Any questions here? So we don't have that much time, so let me immediately go to the last theorem, and then we probably solve a little bit more interesting problems if we have time. So the last one is also very nice, which is not trivial at all. Can you guess that if I give you that 3 sides of one triangle are equal to 3 sides of the other triangle? This is non-trivial that these two triangles are the same copy. Because you might think that what is the guarantee that the angles are also the same? Because we know, might be, you think that I can just, change the sides without rotate the sides without changing the sizes, and it still make another triangle. But this theorem that I want to talk about here tells you that no, that cannot happen. If 3 sides of one triangle are exactly equal in size to the 3 sides of the other triangle, definitely these two triangles are congruent. And I think now you should be able to tell me why. This is also nice to understand based on the book. I really enjoy the way that they presented it here using similarity to go for congruency. Okay, so let me just draw another. This is the final theorem that you need to know. Theorem number 3. And this is called side, side, side. No angles involved. Yes? Okay, so let me just draw a picture here for you again. A figure. A, B, C. Yeah, I have to draw a copy, more or less the same copy here. M and P. So now, what pieces of information I provide for you? I tell you that I measured side AB. It is equal in size to side MN. And I tell you that the side AC, I measured it. It is equal exactly with MP. And then I measured this one. This is equal to this one. I didn't have any protractor. I didn't have any protractor to measure the angles. I just had a ruler and I was able to measure the size of the sides. That's it. And then I see that they're equal. I want to conclude that they are actually congruent. It is not possible. Definitely this angle should be equal to this angle. This angle should be equal to this, and this angle should be equal to this. It's not possible that this is not the case. Okay, so what is my pieces of information? So let me write it in this form for you. So I know that AB is equal to MN. I know that AC is equal to MP. And I know finally that BC is equal to NP. I am telling you that SSS tells you that this triangle on the left is congruent to the triangle on the right. This is the content of this third and last theorem. This uses that similarity theorem, which is not very common. So I told you that there are two theorems for similarity. One was very famous. It was angle-angle. And do you remember what was the other one? I just mentioned it in the beginning.
Angle, side, angle?
No, angle, side, side. No, that is for congruency. Don't mix these two concepts together.
Oh, for
similarity. One of them was angle-angle, which is 99% of the problems use that theorem.
Staley's theorem?
No.
What's the similarity? It wasn't.
No, but this is important to know. Two theorems. The ratio of the sides are equal. If the ratio of the sides from one to the other are equal, then I can conclude the congruency. So tell me here. Okay, let me ask you what you tell me here. If I give you this piece of information, which I have already given to you, so can you tell me what is AB over MN as a fraction? What is this?
It's 1.
It's 1. And then what can I conclude about this ratio?
It's 1.
It's 1 again. So AC over MP is equal to 1. And then I can conclude the same thing here. BC over NP is also equal to 1. But now I know that three fractions, all of them are equal to 1. So it means that all of them are also equal together to each other. So AB over MN is equal to AC over MP, and it is equal to BC over NP. This is probably not very famous theorem that you might forget. If you go back and review the lesson, there were two theorems. Angle theorem for similarity and equality of the corresponding sides, the ratio of the corresponding sides, equality of them. From here, I can conclude that the triangle ABC is similar, not congruent yet, similar to triangle MNP. Yes?
Yeah.
But now, if I tell you that this triangle is similar to this triangle, what you can conclude about the angles?
They are the same.
They are the same. And that is the missing information that I needed. So here, I can conclude that because they are similar, the angle A should be equal to angle M, and the angle B should be equal to angle N, and finally, the angle C should be equal to angle P. Now, you told me equality of sides. I myself was able to conclude equality of angles. So all the sides are equal. You gave it to me. All the angles are equal. I got it myself. So now can I conclude that the triangles are congruent?
Yes.
Yes, because every piece of one of them matches with the corresponding piece of the other one. and then you need to finalize it. Okay? So that is the last theorem that we just discussed about that. So let us review. So there were 3 theorems, yes? What was the first one? Angle, you just tell it. Side, angle, side.
Yeah.
That was the only one that we convinced ourselves by moving the triangle and put it on top of the other one. That was the idea for proving. Then we learned about the opposite situation, 2 angles and the side between them. I used similarity to prove that. And the last one is the equality of 3 sides from one by the other one. Again, we use the idea of similarity. Yes? In the previous one, we used angle theorem for similarity. Here, we just use a little bit obscure one. Usually, people doesn't use this theorem. Most of the time, in similarity, angle theorem comes into the game. This is one of those cases that we use the other theorem. Yes?
Yeah.
Okay. So, for example, one of the famous applications of this is if I tell you that I have 2 right angle triangles, only 2 sides, the hypotenuse and one side from one matches with the hypotenuse and one side of the other one. So let me just tell you this. This is a good problem. So here you can, you should be able to solve it in 2 different ways. Okay. So here, I give you a right angle triangle. Let me call it ABC. And I give you another one. Of course, I have to draw it exactly the same because at the end, it becomes the same. But let me just pretend that we don't know. So M and P. I tell you that I measure this AB. It is equal to MN. I'm giving you this. I take my ruler, measure this one, it becomes equal to this. I measure this hypotenuse of the left one, it becomes equal to the hypotenuse of the right-hand side one. That's it. So I tell you that these 2 triangles are right angle triangles, and I just give you that this side is equal to this side. This hypotenuse is equal to the hypotenuse of this one. Can I conclude that, based on these pieces of information that you see, can I conclude that this is congruent to this one? Yes, Aaron?
Yes,
Why?
because side angle side, we have 2 sides and 1 angle.
No, be careful. That is the reason that
Why?
I wanted you don't confuse. 2 angles. What is the theorem that you are comparing? You are saying 2 sides and angle between them. I am emphasizing it so many times. I will come to you. Even though I have 1 angle of this equal to 1 angle of that, and 2 sides of this equals to 2 sides of that, don't be in hurry. If you just conclude this is side, if you say that this is side, angle, side, this is wrong. Because even though you are right, I have 2 sides from this, 2 sides from that, 1 angle from this, 1 angle from that, but this angle is not the angle between them. Be careful. So this is SA should be sandwiched between these 2 S's, yes? This is why you cannot use it immediately. This is a very simple example, but a very instructive example, because you realize this angle being between is extremely important, so we cannot be in hurry. Okay, Cameron?
It's a right triangle, so you can use Pythagorean theorem and you can conclude that the other side is the same.
Yeah, exactly. So what we say, let us consider this to be A, little c, little b. And let me consider this little m, little p, little m. So you are telling me that, so first of all, I know that a squared, so let me write my information. You told me that c is equal to p. You also told me that a is equal to n. So far, so good. But I also know something in right angle triangle, and that is the Pythagorean theorem. Yeah. So what is that? It tells me that a squared is equal to b squared plus c squared.
Yeah.
Yes. If I ask you what is b squared, you would say b squared is a squared minus c squared. Yes. Do you agree? This is just the Pythagoras theorem. And I just moved, what I did, I moved c squared to the left. It becomes a squared minus c squared is equal to b. I wrote it the other way around. Yes? And now let us do, can I use Pythagoras theorem here? Yes, because that's also a right angle triangle. So m squared is equal to what? P squared plus n squared. Now let me ask you something. Now here I am looking for n squared. So n squared becomes m squared minus p squared. Agree?
Yeah.
But now you told me that m and a are the same. And you told me that P and C are the same. So instead of this M, I replace A, I substitute A, and then instead of this P, I substitute C. So here, let me just write it here. This implies that because M is equal to A and C is equal to P, I can write n squared is equal to, instead of M, I put A, instead of P, I put C. Now what happens, it's very nice. Let us call this number 1, number 2. So if I compare number 1 and number 2, what can I conclude? This tells me b squared is equal to a squared minus c squared. This tells me n squared is equal to a squared minus c squared. So it means that b squared and n squared should be equal. So b squared is equal to n squared. And then the consequence of this, because b and n are positive numbers, so it means that b is equal to n. Now, I have c equal to p from the beginning. I have a equal to m from the beginning. I concluded that b equals to n now. So 3 sides from the left-hand side matches with 3 sides from the right-hand side. So this is side theorem.
Or
Yes?
side angle side, because now we have C and B equals to P and
Yes, that is also true. Yes, in this stage you can do that. Yes, because what you are saying is that because now we know b is equal to n, instead of using side, I can say that c is equal to p, b is now equal to n, and now we know that this angle is between these two is 90. So that's of course true. So that's your choice if you want to go in this direction or that in that direction. But in the beginning you were not able to do that. This is a very simple but instructive example to teach you this, that you are not allowed to do.
Is this a C level question?
Yeah, might be. That's a C level question. So is that understandable for everyone, every person at home? Yes?
Yeah.
If you have questions, please let me know. Okay, let me play a little bit with this right angle triangles. So I didn't completed this. I just talked about the solution orally, but you need to complete it. So the completion means that, for example, let us at least write C is equal to P, A is equal to M, and B is equal to N. So I chose to write side because I want to use this theorem. So the triangle ABC is congruent to the triangle MNP. Okay, but you are completely right. You can, at this stage, you can also use side angle side. Okay, let me give you another piece of information to understand these theorems better. I will give you the same 2 triangles, right angle triangle, but now I change the pieces of information that I provide for you. So here I give you this triangle, ABC, and then let me try to copy and paste somehow here this, and then I give you this is M, N, P. Now what I want to say to you, I will tell you that the hypotenuse I measure is equal to the hypotenuse of this. And then I measure just this angle. It becomes equal to angle N. Is it enough for me to conclude that these 2 triangles are similar?
No.
Yes, you understand, your understanding is correct, but the answer is yes.
Oh, come on.
Yes, you are good that you understand that we cannot do that. Might be you say this is angle side. So you understood it correctly. This is not that theorem. Why? Because this is angle, but it should be the side between them. Do you remember I intentionally wrote angle, side, angle. But can I say that, okay, this is trivial because this is angle, angle, side, angle? You said no, this means that this is not trivial. Is that understandable? So if you write in the exam, because this one is equal to that one, this one is equal to this one, and this one is equal to this one, I use ASA and conclude that these are congruent, that is wrong. But coincidentally, it happens that we can cook up a better argument to show that yes, still they are congruent. Can you cook up that argument?
I think that if you add A, B, and C angles, they will be the same as M and P angles.
Yes. Why?
And, well, it's, because
Yes.
it's a triangle.
Maybe if we know two angles of a triangle, we know the
third one automatically
Yeah.
should be the same.
And
That's
then
the
we can
idea.
use
Yes,
B and
exactly.
C and the one.
So be careful. This is a very simple example. Let me tell you, let me write this. I want you to write it somewhere and cross it over. If in the exam you say that angle A is equal to angle N, it is true. I agree with you. This is true. If you tell me that angle B is equal to angle N, I agree with you again. That is also true. If you write BC is equal to NP, that is also true. But if you say that because of angle, side, angle, I can conclude that these two triangles are congruent, then you will lose all the points. So just write it and cross it over. So everything you wrote on the left-hand side is 100% correct. But based on angle, side, angle, you are not allowed to conclude that because it means that the side should be sandwiched between the two angles. But the angles are these two angles. The side including them is just this side, which we don't know if they are equal. But as Aaron said, that is completely right. If this angle is equal to that angle, and this angle is equal to that angle, the third angle automatically become equal. Yes? Okay, so let me write it here. So you need to convince this. So you would say that angle P plus angle P plus angle N should be 90. Yes? In a right angle triangle, the sum of these two acute angles should be 90. And then you write that, for example, angle B plus angle C is equal to 90 as well. So if this sum is 90, this sum is 90, it means that these two sums are equal. But you told me that angle B is equal to angle C. So angle B is equal to angle N. So I can eliminate this from both sides, because they are equal. Now the conclusion is that angle P is equal to angle C. Now let me change the color here. So this one, I realize that this angle is equal to that angle. Now can I use ASA theorem now?
Yeah.
Yes, based on these two angles and the side between them. Yes, this is now correct. So you have to write this, convince me that the third ones are equal, and then when you are done, what can you conclude here now? You have to write it again in this form. You would say that angle B is equal to, and now you should say now, angle B is equal to angle N. You told me from the beginning. You told me that side BC is equal to side NP. You told me from the beginning. And now I myself concluded, based on the information that you provided for me, that angle C is equal to angle P. Now I can safely write ASA situation. Yes? Let me finish this. Yeah. And then this becomes the triangle ABC is congruent to triangle MNP. These extreme cases, I also have it in my memory. So if one side and hypotenuse are the same with the other one, they are congruent. This is also an extreme case. Just a hypotenuse and one acute angle, if they match, they are also congruent. Of course, the proof is very simple, but I think these special cases deserve to be in your memory. Yes.
If you have a triangle, and if you have two triangles and
Yeah.
all the angles are the same, is there an angle theorem?
No, because you can imagine you can have a very small triangle with a very big triangle if you zoom in or zoom out. So then, for example,
they're similar but not.
They are similar
Okay,
but
but
not
not
congruent.
congruent.
So the equality of all the angles is not enough to conclude that, but equality of three sides is enough to conclude that the triangles are congruent.
Okay.
Okay, so that was the last piece of lesson, and the exercises are on page 153 and 154. I think you have to work at home for that. And then on Friday, you have the chance to ask me questions. And on Monday, we will have the test. Because it's a little bit short time, I will just stick to the problems in the book. Okay, and might be I can give you. There are some good problems I have already written on a Schoolsoft on blue pages. So everything, including a figure. So there are some problems related to those parts that I have omitted. I didn't teach them. So, but the problems with pictures are the problems that you can solve them. So if you want to have more exercises, please think about it. Yes.
What is the test mostly about from chapter 4?
So there are two parts. One part is analytic geometry with coordinates and things like that, and then the other part is circles. And then what we learned about circles and the angles inside the circles. And then we learned about similarities, and now we learned about congruency. So 3 topics here and 1 topic, analytic geometry, 4 topics.
But which of them is most?
No, I will try to give them equal weights.
Okay.
Somehow. Yes, it is hard to adjust exactly everything, but I will try to do that. Okay, thank you very much. I end this stream here. I will be available on Zoom if you have any questions. Otherwise, we'll end the meeting. Thank you.